So we can tailor expand the function of x around this expectation value of x. Right? Expanded around this, it would be this plus. Okay. So the derivative evaluate the okay, so these stand for higher order terms. Now, if I were to take the expectation value of this expansion, okay, now the first thing is that this is just a number, so it gives you the classical quantity. Okay. So over here, this is the prediction of classical mechanics. Now the prediction of quantum mechanics is, we have on the left-hand side, this is certainly true. Okay, we have the classical force. Okay, and then the force linear in x. Okay, this term. When I take the expectation value, it's going to vanish, right? Because the expectation value of x minus this expectation is going to be 0. So I'm only left with at least the second order term. Oh, sorry, I should put the expectation value here. Right? Okay. And this is in general not 0. So what have we learned here? What if now I had a function, I had a force that was linear in x? Okay. So that the second derivative of the force with respect to x is going to be 0. Right? Then the quantum mechanical equation for the time evolution of the expectation value is going to completely agree with the classical term. But now, when I have nonlinear forces, I'm going to have deviations in quantum mechanics, even in the expectation value sense, to classical mechanics. Right? So, what is a linear force? So I'll say that F is equal to kx. What does that mean? This is harmonic motion, an oscillator, a harmonic oscillator. So the harmonic oscillator, the potential, since the force is linear in x, the potential will be quadratic in x. So for the quantum mechanics, this is why the harmonic oscillator is interesting. There's an interesting connection between quantum mechanics and classical mechanics, because on average, the operators are going to behave classical mechanically, even though it's in quantum mechanics. But that doesn't mean for the harmonic oscillator, there's no difference between quantum mechanics and classical mechanics, because don't forget that we're doing expectation values here, and we're not considering the operators or the state by themselves. Expectation values are both a function of the state and the function of the operator. Okay?
You may want to explain what you mean by derivative with respect to an operator. S hat is an operator.
Okay.
Differentiate with respect to an operator. What does it mean?
Let's say that we have some potential, right? And the potential written in classical mechanics, it looks like 1/2 kx squared. So it's a very nice potential, right? So now, if I want to compute the force, I compute it symbolically by taking the derivative with respect to x. So now in quantum mechanics, how do you promote a classical quantity to a quantum mechanical operator? You replace x by x hat. You replace p by p hat. Okay, and these things are Hermitian, so no problem. But sometimes you get things like maybe you have some operator that looks like xp. Right? Maybe you have a value that looks like this. You can certainly promote this to quantum mechanics by saying, all right, let's just do this. But if this was inside the Hamiltonian, what would happen to the Hamiltonian? Right, if the Hamiltonian contained a term that was like this, okay. Is this term Hermitian? No, right? No. Okay. Why? Because X and P don't commute. So the Hamiltonian constructed this way would not be Hermitian, and you cannot do quantum mechanics that way. So when you encounter this special case, all you do is you construct. Okay, you construct the Hermitian part of it. Okay. And why does this work? Let's not worry about that at the moment. So this is in general how you would promote this to quantum mechanics. And then when you take the derivative of an operator function with respect to that operator, you just do everything symbolically. Pretend it's not an operator for a second. Okay. Do it symbolically, and then write down the equation, and then promote it to quantum mechanics again. Okay. Promote it to operators again. That's one. But the important message is here is that if we look at this equation, for the case of no force, constant force, or linear force, okay, which is the free particle, a triangular well, okay, constant force would be a triangular well, right, and the harmonic motion of a quadratic potential, the expectation value of the quantum mechanical operators do not differ from their classical counterparts. Okay, so this is the important thing. But for nonlinear forces, when nonlinear forces are involved, quantum mechanics and classical mechanics, they're completely different. Okay, so this is the correspondence between the quantum mechanical equation of motion with the classical equation of motion, and this is the general. The more you can generalize this to more than one E, and that is called the error stress. And this is just a simple example of the error test. So quantum mechanics, you would expect, people always say that, the average, when you average in quantum mechanics, you get classical behavior. But that is not actually the case, because as you can see in nonlinear forces, they don't even agree on average. Okay. Are there any questions?
So like, for example, you wrote like a non-restoring force, so like, would you actually even really have a normalized wave function? But like, what happens if it was?
What happens if the potential looks like this?
Oh, so like, would you even be able to use this?
You're right, because let's see, you would still be able to use this. I don't see the problem with that, but you wouldn't. This would be, you wouldn't have any bound states, but you just have scattering states. Yeah.
Okay, so we can expectation values for non-bounded states. Okay.
I think one way to think of differentiating with respect to an operator is to have the operator work act on the eigenvector of the operator, and then it becomes a scalar differentiator, and then remove that operator.
So what Professor Chu is getting to is, remember in the beginning of the class we taught you what is the meaning of a function of an operator, or what is the meaning of a function of a matrix. So if I was trying to compute this, okay, and you have no idea how to compute this, well, imagine this operating on some eigenstate of the x operator, which is just x, right? So that would replace each of this by the eigenvalue x, right? So then it turns into just differentiation of just a real value function. Many ways to think about this. So are there any questions? This is a very important part. All right, if there are no questions, I'll give you guys a 5-minute break, and then we'll come back and talk about chapter 6, the approximation method.